A mosaic is a space-filling tiling that creates patterns from easily distinguishable cells without overlaps or gaps. More formally speaking, mosaics are divisions of any space into countable disjoint closed subsets that cover the whole space, where each subset is compact, non-empty, and shares its entire boundary with its adjacent subsets. The study of mosaics dates to antiquity. In ancient times, mathematicians focused on two main methods of analysis, algebraic and geometric. Geometry was seen as the study of spaces and what they contain. The ancient Greek philosopher Plato used mosaics to theorize what the building blocks of the universe looked like in relation to the 5 Platonic solids. From molecular to global, at some level of structure, we can see mosaics in almost everything. The ones we are most familiar with are found in architectural history. Alhambra contains many notable examples, with mosaics depicting all of the different geometric frieze and wallpaper groups. In daily life, they are most commonly found in mud cracks and rock formations. This even extends all the way out to the pattern of Earth's tectonic plates. The study of mosaics could even lead to being able to differentiate materials, like trying to find fossils in overview pictures of dig sites. When we start looking at examples on increasingly smaller scales, we notice more regular mosaics in the grouping of cells and molecular crystalline structures. Like palladium chromite as an example of a regular, triangular mosaic. Normal convex mosaics. We focus on a subgroup of mosaics that are exclusively made up of convex polygons. Convex means that given any 2 points in a cell, the straight line defined by their distance is completely contained in the cell. To define normality, we state the existence of an A and B, where A is greater than 0 and B is greater than A, such that each cell contains a ball of radius A and is contained in a ball of radius B, creating finite upper and lower bounds, constricting the cells to not grow or shrink infinitely, like in a fractal pattern.
Building upon these requirements, we will define several properties that can be used to classify similar mosaics. By convexity, the cells of the mosaic will be convex polygons, and the nodes of the mosaic will be the vertices of these polygons. A node is said to be regular if it is a vertex of every cell it is a part of, and irregular if it lies along a flat edge of a cell. Define the order of a cell to be the number of vertices it has. Similarly, define the order of a node to be the number of cells it is a vertex of. V and N will refer to the averages of these values taken over the whole mosaic, when necessary, limits taken over expanding disks. The letter P is used to denote the proportion of regularity, defined to be the number of regular nodes divided by the total number of nodes. The domains of N and V define the axes of what is called the Schläli plane. The ordered pair NV is often referred to as the Schläli symbol, and represents a point on the Schläli plane. The accompanying poster gives arguments based on plane geometry and combinatorics to first prove there is a compact domain on the Schläli plane, wherein all plane mosaics must exist. The bounds on this region come from analyzing the proportion of regularity and the average angle around each node. Then to describe 2 moves that can be used to modify a base mosaic to realize any point in this domain. N and V have an inverse relationship based on P. The first move is to change an irregular node to a regular node. The second move is to reduce the order of a cell without changing the proportion of regularity. The first move will adjust P while sliding the Schläli symbol along the minimum N bound. The second will slide along the curve given by the now fixed P value to reach the desired NV. The Schläli plane provides a combinatorial way to classify the structure of mosaics.
Structure is determined by environmental conditions. Analyzing an existing structure can provide a suggestion of the conditions that formed it. This can be seen in 2 common algorithms used to generate mosaics. One is Voronoi diagrams, where circles expand from points and intersect to form boundaries. This creates large ordered cells and mostly regular vertices, tending towards the uppermost region of the Schläli plane. The other is Gilbert tessellations, where lines propagate out from points until they are obstructed. This creates low-ordered nodes and many irregular vertices, tending towards the leftmost region of the Schläli plane. These two methods create qualitatively different mosaics, and as they are in different regions of the Schläli plane, they are combinatorially different as well. With further analysis, position on the Schläli plane may prove to be a helpful indicator of the local forces that formed a mosaic. Real examples of this can be seen in bubbles and broken glass. Currently, grain analysis of metals consists of measuring the size of the grain, but size is not a reliable indicator of shape. The Schläli plane provides a measure of combinatorial structure. With further research, this measure may prove to be a helpful indicator of some material properties. Here are a few hand-calculated NV values for specific grain samples. In conclusion, mosaics are everywhere. Using the average order of cells and nodes, they are plotted on the Schläli plane. There is a bounded domain on the Schläli plane where normal convex plane mosaics must exist, and every point in that domain can be realized. There are qualitative and combinatorial differences between mosaics, and perhaps these differences can be used as a tool for analysis.